All right, in this worked example, we'll be looking at the learning objective, determining the frequency of a sound wave using a cathode ray oscilloscope. It just so happens we have a nice little display of a sound wave on the screen of a cathode ray oscilloscope right here before us. It tells us that the time base of the CRO is set at 2.5 milliseconds per centimeter. So if the goal of the oscilloscope is to scope an oscillation to see a wave, then you need something that looks like this. You would adjust the time base setting until you saw a nice waveform. Then we can use the time base setting and say, okay, well, if each one of these centimeters is 2.5 milliseconds, I've got 2.5 milliseconds per centimeter, but how many centimeters is a wave? And so I can look at 1, 2, 3, 4 centimeters is where I've got an entire wave. I could measure it from here, crest to crest. In other words, this is an entire waveform. So from crest to crest, 1, 2, 3, 4 centimeters. Or from trough to trough, this is an entire waveform. 1, 2, 3, 4 centimeters, right? So I've got 4 centimeters per wave. It's kind of like the wavelength on the display, but it's not really the wavelength of the sound wave, right? I've just used my technology to convert the sound wave frequency into something I can see, scope on my device. And I can count out that there's 4 centimeters per wave. Now I can use this to cancel out centimeters. So there's 2.5 milliseconds per centimeter. And you could really start with that. If you know the time-based setting, you could start the calculation by going, if I've got 2.5 milliseconds per centimeter, and now I look at 1, 2, 3, 4 centimeters per wave, you see it doesn't matter what order you multiply these two. The commutative property of multiplication, little academic language review, you're welcome. Now we've got how many milliseconds per wave. You may recall that if we know the time per wave, we call that the period of the wave. And if we want to know the frequency, there's a simple relationship between period and frequency. So we're kind of home free. 4 centimeters per wave times 2.5 milliseconds per centimeter means we've got 4 times 2.5. We've got 10 milliseconds per wave. That's the time period. So if I want the frequency, I'm just going to do 1 divided by 10 milliseconds. Don't forget about the metric prefixes. We saw that in another example. Knowing those metric prefixes is very important. One divided by 1,000 is 1,000. So I must have made a mistake. Where did I go wrong? One divided by, oh, I think I did 1 times 10 to the 3 instead of 10 times 10 to the 3. 1 divided by 10 times 10 to the 3. So I think it's 100 hertz because I got 1,000 when I calculated, but 1 divided by 10 times 10 to the 3. Sorry. 1 divided by 100. 10 times 10 to the negative 3 is 10 thousandths is 100, right? So 1 divided by 100 is 100. So that would be 100 hertz, kind of a low frequency. And so we could deduce the frequency of a sound wave to answer today's essential question. How can we determine wave properties using an oscilloscope? Well, we could determine the property frequency the way I just showed you there.